Today we will talking about introduction to hypothesis testing, and this is the outline. Okay, we will I will try to begin this hypothesis testing to simple hypothesis testing and the example. We said before that estimation of parameters was one of two major areas of statistics. Now let us turn to second major area of statistics, hypothesis testing. A test of statistical hypothesis is a procedure for deciding whether or not to reject the hypothesis. What is statistical hypothesis? A statistical hypothesis is an assumption about if x is continuous, or px if x is discrete. Let's look at an example. A buyer of light bulbs bought 50 bulbs of each of two brands. When he tested them, brand A had an average life of 1,208 hours with a standard deviation of 94 hours. Brand B had a mean life of 1,282 hours with a standard deviation of 80 hours. Are brand A and B really different in quality? This is the question. And to answer these questions, we use hypothesis testing. We set up two hypotheses. First, called the null hypothesis. H null is the hypothesis of no difference. H null mean of product A equal mean of product B. The second, called the alternative hypothesis, is H alternative is a hypothesis that there is a difference mean of product A not equal mean of product B. On the basis of sample of 80 from each of the two population of light bulbs, we shall either reject or not reject hypothesis of no difference. In statistics, we always test the null hypothesis. The alternative hypothesis is not default winner if the null hypothesis is rejected. We never could accept the null hypothesis. We simply fail to reject it on the basis of evidence in hand. Now we need to procedure to test the null hypothesis. And a test of a statistical hypothesis is a procedure for deciding whether or not to reject the null hypothesis. There are two possible decisions: reject or not reject. This means there are also two kinds of error we could make. The two types of error are shown in the table below. This decision will reject H null when H null are true. The probability of is alpha, and this is the type error 1, and sometimes we reject H null, and the reality is H null is false. The reality H null is false. It is correct decision. And do not reject H null, and the reality H null is true, correct decision. And sometimes we do not reject H null, and the reality H null is false. And we said that this is the type error 2, and the probability is beta. If we reject H null when H null is true fact, then we make type 1 error. The probability of type 1 error is alpha, and is now we need a decision true that will make the probability of the two types of error very small. The problem is that the rule cannot make both of them small simultaneously. The one type of error the experimenter has under his control is alpha error. He can choose the size of alpha, because in science we have to make the conservative route and never claim that we have found a new result unless we are really convinced that it is true. We choose a very small alpha, the probability of type 1 error. The among all possible decision rules given alpha, we choose the one that makes beta as small as possible. The decision rule consists of a test statistic and a critical region. Decision rule consists of a test statistic, and critical region where the test statistic may fall. For means from a normal population. The test statistic is T equal x bar A minus x bar B per S standard deviation, and equal this, where the denominator is the standard deviation of the difference between two independent mean. The critical region is a tail of distribution of the test statistic. If the test statistic falls in the critical region, its null is rejected. Now, how much of the tail should be in the critical region? They depend on just how small you want alpha to be. The usual choice is alpha is equal 0.05, but in some very critical case, alpha is set at 0.01. Here we have just a non-critical choice of like poles. So we will choose alpha equal 0.05. This means that the critical region has probability equal 0.025 in its tail of the T distribution. For a T distribution with 0.05 to 5 in each tail, the critical value of t equals 0.95, the same as z, because the sample size is greater than 30. The critical region then is observed value t equal rather than 1.9596. In our light bulb example, the test statistic is like this: 1282 minus 1208 per this standard deviation, and we get 4.23. Now 4.23 is a much greater than 1.996, so we'll reject the null hypothesis of no difference and declare that the average life of the B balloon is no longer than that of the A bulls. Because alpha is 0.05, we have 95% confident in decision we made. We cannot say that there is a 95% probability that we are right, because we are either right or wrong and we don't know which. But there is such a small probability that the t will land in critical region if its null is true, that if it does get there. We choose to believe that its null is not true. If we had chosen alpha 0.01, the critical value of t would be 2.58, and because 4.23 is greater than 2.58, we would still reject its null. This time would be with 99% confidence. How do we know that the test we use is best test possible? We have controlled the probability of type 1 error, but what is the probability of type 2 error is the test? Does this test minimize its subject of the value of alpha? To answer this question, we need to consider the concept of test power. The power of statistical test is the probability of rejecting H null when H null is really false. Thus, power is 1 minus B. Clearly, if the test minimizes power, it minimizes the probability of type 2 error B. If a test minimizes power of given alpha, it is called an admissible testing strategy. Before going further, we need to distinguish between two types of hypotheses. A simple hypothesis is one where whether the value of the parameter under H null is specified constant and the value of the parameter under H alternative is a different specified constant. For example, if you test H null, mean is 0 versus H alternative mean is 10, then you have a simple hypothesis test. Here you have a particular value for H null and a different particular value for H alternative. For testing one simple hypothesis H alternative against the simple hypothesis H null, a groundbreaking result called the Neyman-Pearson lemma provides for the most powerful test. this lambda equal L theta hat alpha per lambda hat null theta lambda theta hat null. Lambda is the likelihood ratio with the each alternative parameter MLE in the numerator and the each null parameter MLE in the denominator. Clearly, any value of the lambda rather than 1 would favor the alternative hypothesis, while values less than 1 would favor the null hypothesis. Basically, this likelihood ratio says that if there exists a critical region A of the size alpha and a constant k such that this L alpha per L null is multiplying of fxi given theta alpha per this and rather than equal k inside A and this, then A is a best or most powerful critical region of size alpha. Consider the following example of a test of two simple hypotheses. A coin is either fair or has pH is 2 per 3 under H null, pH equal 1 per 2 and under H alternative, pH is 2 per 3. The coin will be tossed 3 times and a decision will be made between the two hypotheses. Thus X is number of heads 0, 1, 2 or 3. Now let's look at how decision will be made. First, let's look at the probability of type 1 error alpha in the table below. H null is pH 1 per 2 and H alpha is 2 per 3. This is X and the probability. Now what should the critical region be? Under H null, if X is 0, alpha is 1 per 8 under H null. If X is 3, alpha is 1 per 8. So if either the two values is chosen as the critical region, the probability of type 1 error would be the same. Now what if H alpha is true? If X is 0 is chosen as the critical region, the value of beta is 26 per 27, because that is the probability that X not equal 0. On the other hand, if X is 3 is the chosen as the critical region, the value of beta is 19 per 27, because that is the probability that X not equal 3. Clearly, the better choice for the critical region is X is 3, because that is the region that minimizes beta for fixed alpha. So this critical region provides the more powerful task. In the discrete variable problem like this, it may not be possible to choose a critical region of the desired alpha. In this illustration, you simply cannot find a critical region where alpha is 0.05 or 0.01. This is seldom a problem in real-life experimentation because n is usually sufficiently large so that there is a wide variety of choosing for critical regions. This problem, to illustrate the general method for selecting the best test, was easy to discuss because there was only a single alternative to each null. Most problems involve more than one single alternative. Such hypotheses are called composed hypotheses. Okay, I think that's all. We will continue in another time. Assalamualaikum warahmatullahi wabarakatuh.